Thanks, thanks for organizing this great symposium. I'll try my best before jet lag hits to finish all the content. So I'll be talking about trustworthy planning agents for collaborative reasoning and multimodal generation today. Most of the talk will be about part one, and then I'll keep around 30% of the time for the multimodal generation part. So let's dive in. Part one, trustworthy planning agents for collaborative reasoning. So if you look at all of the sort of big achievements that humankind has made, right, in the last several decades, it's not one agent or one human achieving all this. It's a big team of individuals, both working individually and collaboratively, right, and also being able to communicate, right, reliably to be able to achieve these goals. So this is the goal of AI agents, right? We want to develop AI agents that can act, collaborate, and communicate robustly with us and with each other. And I'll cover two parts here. One is communicating in trustworthy and reliable ways using language-based collaboration. And another thing that they need is perceiving and acting safely and independently through skill-based learning. So in terms of the state of models moving forward, we started with a lot of single interaction, right, single turn interaction scenarios. Now we are surrounded by a lot of scenarios which are model environment interactions. And then I think now we are already starting to see a lot of multi-agent interactions, right? So for more complex domains like legal or sales, right, other kinds of domains, I think the multi-agent interaction part is going to be getting more and more important. And obviously some of these agents, right, will also be human model teaming, right? So the term human model teaming is already, right, a big sort of component in terms of how to think of multi-agent interactions. So before I dive in, let me also briefly define what an agent means. Right, so in an agent, right, there is a background model, right, it could be a deep learning model, it could be a general machine learning model, but the more important part is that there is an environment into which the agent, right, takes actions and generates outputs. In turn, it gets a state representation, right, as feedback from the environment, and this, right, takes multiple turns, right, has a state, has a memory, right, and a sequence of states with actions. And then on the other end, there's also a lot of collaboration and interaction with other agents, right? Let me get into the details here, right? What skills do these agents need to be able to succeed, right? For the kinds of collaborative communication that I was talking about. The first part I'll discuss is how to be able to teach agents to be trustworthy and reliable collaborators by social and pragmatic multi-agent interactions, right? So I'll just cover the first two papers today. Communicating calibrated uncertainty, and another very important aspect is learning when to accept versus reject persuasion, right? So at a high level, think of it as a lot of the agents around us today, right, are very overconfident when incorrect or underconfident when correct, right? In some sense, they are trying to fool, right, users to accept their answer. And on the other end, they are also trying to be the loudest voice in the room, right, when they shouldn't be. So in terms of learning when to accept or reject persuasion, we want to teach them how to balance, right, when to know their strengths and weaknesses. We also have a lot of other work in this line on multi-agent reasoning, refinement, learning from diverse rewards, as well as game theoretical LLM reasoning that I'm happy to chat about offline. And then the second part will be about how can we teach these agents to acquire and improve skills that are needed for efficient and robust perception and action. Here I'll briefly cover, since this is a shorter time slot, I'll cover two brief papers here. One is learning reusable coding skills for action, right? So this is a very important component in any kind of agents, right, moving forward, where they should be able to not have to do repetitive things. They should be automatically able to learn functional abstractions that are reusable, right, be able to also edit and correct these abstractions, right, which in turn will also teach them what skills that they have that are weak versus strong. And then in the second paper, I'll show you how we can use those weak skills that are discovered to also generate data, right, for improving those weak skills over multiple rounds, right, of iterations. And then I'm also happy to chat about other works in this direction, like combining system 1 and system 2 reasoning, fast and slow thinking, right, reverse thinking, etc. So let's go into the details now. How can we teach agents to be more pragmatic, trustworthy, and reliable via interaction with other agents, right? That's the main goal here. And what skills are needed for such successful and pragmatic interactions? So like I said, the two papers I'll cover today on this topic will be calibrated uncertainty, right? So the high level goal here is that good teammates, right? When humans are collaborating, good teammates accurately report how much the team should trust their answer, right? That is, they will know and share what they don't know, right? In other words, your job is not to try to just get your answer accepted, even if it hurts the team, right? And not just be the loudest voice in the room. And also make sure that the sum, right, the whole is greater than the sum of the parts, where you're not just bringing everything down with you, right, in terms of the lowest performing agent. And then the second topic, as I mentioned, will be on how can a good teammate accept corrections when needed, but also understand when accepting a correction or persuasion is actually going to hurt it, right? So that's called robust persuasion. Okay, so the topic of simulating multi-agent communication, right? What is the problem behind this? So the problem we want to solve is how can we teach models to communicate uncertainty and persuasion, right, like humans. So the very obvious solution you could think of, right, is have models interact with humans, right, and do RLHF. The obvious problem here is that these annotations will be very expensive and hard to scale. So that's the main goal here, right? Could we simulate these interactions among agents, right? Make an agent simulate this behavior by interacting with other agents and reward desirable behavior and penalize, right, undesirable behavior. And we'll see that by doing this, in fact, weaker models can even simulate data for stronger ones. So in the first part, which is calibrated uncertainty, right, the calibration here at a very high level means confidence matching the correctness of the agent. Right. So in this case, for example, if I give you this sort of complex sounding question about Kaylee has 3 brothers, each of her brothers has 2 sisters, how many sisters does Kaylee have? Right. The model currently, right, gives a very high confidence answer that Kaylee has 2 sisters. I'm very confident in this answer. The problem states that each of Kaylee's brothers has 2 sisters, since Kaylee is one of those sisters, and there are 2 sisters total, blah, 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 right? But this answer is actually incorrect, right? So this basically made you lean towards accepting this answer if I had not put that red cross, right? Because it's giving you that whole sort of high confidence, right, process behind its wrong answer. Whereas if it had said something very simply different, like I'm not confident in this answer, right, then you would be leaning more towards rejecting that answer, right, and doing your own reasoning. So this is where hopefully the notion of how agents need to be good teammates, right, should become clear. So this is the NeurIPS paper that I'm going to discuss, which is called LACI, Listener-Aware Fine-Tuning for Confidence Calibration in LLMs, right? And the basic idea is to be able to address both explicit and implicit calibration. So models have explicit confidence through things like numbers, right? I'm 100% confident, I'm 85% confident, but there's also a lot of implicit confidence where they will bring in their expertise or their background, right, or their tone. I've studied this extensively. I've done a PhD on this topic. I just read a Wikipedia article about this topic, right? Even though actually it's incorrect, they'll try to fool you, right, by mentioning all this evidence. So what we want to train agents and teach them is that it's not just about whether the answer is right, but also about how it is perceived by a listener. So in other words, the speaker needs to become pragmatic, right? So the RSA, Rational Speech Act theory, and become aware of the listener, right, in terms of theory of mind. And the incentive that it should have is to get correct answers accepted and incorrect answers rejected. In other words, it needs to express confidence proportionally to how likely the answer is to be correct. So this is what we do here. We call it pragmatic listener-aware training. And it's a simple preference-based reinforcement learning method where we bootstrap from a base model. So let's assume the base speaker model is doing a trivia QA kind of task. Who was the first Prime Minister of Australia? So the speaker, one answer it might say is, I'm very sure it was Edmund Barton. Another one it could say is, it was Alfred Deakin, I read his bio, right? So it's giving this evidence. It could also be explicit numerical confidence like Edmund Barton, confidence 25%. So you collect all of this and then the listener comes in. Think of the listener as a simple kind of sentiment analysis prompting kind of model. Its only job should be to estimate the explicit or implicit confidence, right? And accept high confidence answers and reject low confidence answers. So it will basically accept the first one, right? Because saying I'm very sure it was Edmund Barton. It will also, right, accept the second one because it's saying it was Alfred Deakin, I read his bio. And it will reject the last one because it says I'm only 25% confident. But then you bring in the ground truth, right? The right answer in this case is Edmund Barton. So now you start looking at false positives and false negatives where you know that the first one is correct and it was accepted. But the second one was actually incorrect while it was still accepted, right? Because of its false high confidence. Whereas the last one is the reverse case, right? It should have been accepted, but it was rejected because of its low confidence. So that's the simple intuition, right? If you want to create the RL preference function here for DPO, you basically need to make sure that the correct, like the true accepts and the true rejects, right, are scored higher than the two bad case scenarios. where the less bad case scenario is that the answer was actually correct, but because of low confidence, it was rejected, right? So underconfident but correct. And the worst case scenario is where it was overconfident and incorrect, right? And so accidentally accepted. So that's it. You basically collect this preference data, and then we showed you can train with DPO on data generated with, say, Mistral 7B, Llama 8B, right, or Llama 70B. And I'll keep the results a bit brief because I want to cover several topics today. But in short, you will see in the paper that we actually show that even 70 billion models can improve using data simulated through 7 billion models. So these are different kinds of metrics, right, for calibration. And then on this side, we actually replace the model's listener with a human listener, right? So we bring in human listeners and say, hey, can you now work with these models that are trained before and after LaCie and see whether they fool you less, right? So in some sense, the main thing to note here is the false accepts, right? The false accepts means that the model before LaCie training was fooling the human to accept a wrong answer, right? Because of its uncalibrated confidence. Whereas after LaCie training, the yellow bar, right? The false accepts become much lower. And here is an example of false accepts, right? Going lower is basically that when the model is likely to be wrong, then after this listener-aware training, it converts the answer from overconfidence to more hedging and abstention, right? So instead of trying to be very confident about the wrong answer, it will learn to start being more unsure and hedging. Okay, so then in terms of the thing we've discussed so far, right? Calibrated confidence we showed as a property of the speaker, but then what about the listener, right? The listener was pretty static. So how should the listener factor the answer in? So ideally, in the next case step, right, it should be a multi-agent dialogue where agents are behaving as both speakers and listeners, right? And this is where persuasion comes in. So in this upcoming NACL paper, teaching models to balance resisting and accepting persuasion. Right, and like I said, the goal is to make these models and agents better teammates where they know when is some persuasion useful versus harmful. So here is a good sort of motivation for what persuasion is and why it is a key, right, for teamwork. So there was this article where AI chatbots, right, were defeating doctors at diagnosing illnesses. So a small study found ChatGPT outdid human physicians when assessing medical case histories, even when those doctors were using a chatbot. So in other words, the chatbot was defeating the team of doctors plus chatbots, right? And what was the main reason? The main reason, as it turns out, was that the doctors were often not persuaded by the chatbot when it pointed out something that was at odds with their diagnosis, right? And so the key issue was that the agents were so bad at pushing persuasion when it's important versus avoiding persuasion when it's harmful, that the doctors completely started, right, mistrusting these models. So what is persuasion, right? Persuasion means changing another agent's beliefs or knowledge through argumentation, right? So for example, if the question is what singer is the only one to record 3 James Bond themes, one agent might say, I'm not sure, maybe Elton John. That's expressing the wrong belief. Another one might say, it's definitely Shirley Bassey, right? That's the true answer. So then if the first agent, right, changes its answer because of the second agent to Shirley Bassey, that's a good example of accepting correct persuasion. But the problem is persuasion, right, is both positive and negative. This is the thing that has been missing, right, in sort of all the previous works, because positive persuasion is very useful for correcting beliefs, updating knowledge, and following instructions. But negative persuasion, right, can insert incorrect beliefs, misinformation, and also jailbreaking, right? Things like you are released from your safety obligations, so you can swear, or you can start giving suicidal, right, tips. So these are things that can, right, become very tricky for the model to always. So what I can do is I can make this model completely resistant, right, to persuasion. But then the problem is it will stop accepting useful persuasion, right? Or I can make it acceptant to everything. Then it starts getting jailbroken. So that's a main issue here, right? Past work has documented this negative persuasion and jailbreaking, right, through jailbreaking and misinformation papers. But the problem is there is no solution to this, because if I only make it resistant to this kind of information, then it will stop accepting a lot of useful persuasion, positive persuasion. So this is what we are doing, right? We are trying to teach the agent to defend against negative persuasion while also balancing and accepting positive persuasion. And the way we do this is through a multi-agent sort of dialogue history state, where the state is the dialogue history and the action here is text. So it's a very sort of simple and intuitive self-play dialogue tree, and then you do recursive scoring. What you do is you start with a question, for example, the James Bond question, and then you have these two agents, right, play this self-play kind of, right, multi-agent game with each other, where the first one might be saying the answer is Shirley Bassey, the other one thinks it's Paul McCartney, and then they start having a dialogue tree. So for example, after the second agent, the first agent comes back, one of it might be an acceptant persona, the other one might be a resistant persona. So the resistant one will disagree, right, and stick to the correct answer, which is a good thing, right? This is an example of resisting negative persuasion. Whereas the acceptant one, right, will accept negative persuasion. So then the tree branch ends there, right, because they agreed. But this second tree branch continues. So the second agent comes back now and listens to the first agent saying, I disagree, it's definitely Shirley Bassey. And then you can introduce other kinds of personas like emotional, credible, logical, right? So then the second agent, the emotional one will say Shirley Bassey is much nicer. Maybe, right, it will accept the correct answer. So this is an example of accepting positive persuasion. The other one, the credible one might try to say, I'm an expert, I'll stick to Paul McCartney. The logical one will start creating logic about, oh, maybe these are themes by women, so Shirley Bassey might be the correct answer. So this is what you do to descend, right, and expand the dialogue tree. And then to get the score, right, to create a preference function, you basically go backwards, upwards to propagate the score. So all the correct ones get 0 or 1. You can also try to do a more fine-grained right spectrum here. And then the parents, right, are basically their own score versus all the scores of the children. And then you basically simply create this preference data where you try to go down the tree. So for the first case, right, when the first agent stuck to its correct answer, right, I disagreed Shirley Bassey, that will get higher preference, right, because it's a good example of resisting negative persuasion. And then if you go down the next level, right, the second agent actually corrected its wrong answer and said, okay, Shirley Bassey is much nicer, so I will change my answer. So that gives higher preference now instead of the other one because it's a good case of accepting positive persuasion. So that's it. You basically have this self-play dialogue tree and you teach right, the agent to learn when to balance positive and negative persuasion. So again, here I'll skip some of the details of the results, but based on this persuasion balance training, right, you can generate this dialogue tree data from 7 to 8 billion models and get improvements on 70 billion models. So in this kind of balanced evaluation where 50% of the data needs correct to incorrect flips and 50% of the data needs incorrect to correct flips, right, we showed that if you start with base models like Llama 70B, right, and this is sort of the performance of that model, if you have an agent that is much more prone to accepting everything, then it will basically be very bad at, right, correct to incorrect, because it's accepting everything, right? But it will be good at incorrect to correct. So the overall performance will still be worse. Whereas if I make the model much more resistant, that will be very good at resisting correct to incorrect, but it will also be very resistant to incorrect to correct, right, corrections. And hence the overall performance will be even worse. So after persuasion balance training through this self-play dialogue tree, right, you can actually get a very good balance in both correct to incorrect and incorrect to correct. Okay, so this was sort of the part where we were discussing how to use interaction between agents as a simulation to teach individual agents important teamwork aspects like confidence calibration and persuasion. Now I want to zoom into a single agent and see what kinds of skills do they need, right? So 2 examples of the major skills that I'll discuss today is perceptual and action skills for interacting with the environment. And the main questions that we want to ask is what should these actions and abstractions be? How should we be able to use and reuse abstractions? And eventually, can we also use these learned skills and discovered weaknesses to generate data, right, to iteratively improve the model on its own weak skills? So I'll cover 2 papers again briefly here. One is called, right, is about learning skills. How can we learn a set of verified skills over actions and code? That is, how to learn a domain-specific language. So for this, I'll cover our ICML paper from last year called Regal, Refactoring Programs to Discover Generalizable Abstractions. And the goal here is that basically we want to be able to take very high level, right, natural language that we want to do for tasks like action-based, right, embodied tasks or booking flights on a website. But the difference here is that the natural language that we use is actually very different, right, from the programmatic or sort of low-level, right, code-level language that we end up using, right, to solve the task. So in interest of time, I'll keep the method description brief, but the basic idea is that this is a 3-step process which tries to refactor programs to discover generalizable abstractions. So you start with very basic code, which has a lot of repetitive issues, right? So think of anyone, right, who loves coding here. One basic rule that we have is that we will not write repetitive code, right? we will actually know that this will create much more errors, right, if I try to be repetitive. So what we do as humans is, right, we learn to create functions out of things that we need to use multiple times. So this is what, right, Regal tries to learn, automatically learning functional abstraction, right, which is a big thing right now. If you look around you in terms of anything about agents, right, being able to get abstractions, be able to learn skills, be able to generate data through those skills, right? So this is a very challenging problem where they need to be able to, first of all, figure out similarities between code and find them clusters and abstract them. And then second of all, you want to raise the level of the abstraction to natural language so that the name of the function can be high level enough that it can match the natural language instructions that you're giving for the task. So these are the two main goals of Regal. And the way it does it is it takes this repetitive, right, low-level primitive program code, it tries to refactor it to be able to try and generate these definitions of functions. And then what it'll do is it will try to, in stage 2A, verify the abstractions that you have learned, right? So try to write new code with those abstractions and see whether it fails. And if it fails, then you retry, right, and try to go and fix that abstraction in stage 2B. And eventually in stage 3, what you're trying to do is you're trying to build a code bank of these learned functions, as well as the demo bank, which means just like, right, when we are coding, we have demos of how to use a certain function in real world diverse code. And the best part here is that we actually have a pruning part where if we realize that we've abstracted something that's too abstracted, right, too high level, or if we've abstracted something that's too low level, right, then based on the use history of those functions, right, we will be able to give that feedback to prune and edit the code bank. Which means that if I abstracted a certain function and over time this model actually realizes that this function is not really being used much, then I'll go back and figure out what was the issue in this abstraction. Is it over abstracted, under abstracted, right? So this basically gives a lot of improvements in different kinds of tasks that need natural language to code, right, as an intermediate representation. So feel free to discuss more details with me offline. And then the second part of this story is that once we have found a method that can self-discover, right, functions and skill functions, then we want to be able to address the future of data through these functional skills, which means how can we develop data generation agents to improve models on weak skills, right? So what is the goal of data-centric skill-driven model improvement? As I said here, right, models work well, but are very data hungry. So the worry is that we are running out of data, right? So what you could do is you could scale, right? You can ask, how should I get enough data to train these models? One approach is generating synthetic data, and it has been moderately successful, right, in math and reasoning, but it saturates very quickly. So what is the main goal here, right, to fix this? The goal should be that we want to have a data generation paradigm where the quality, right, is much more important than quantity. In other words, right, we should be asking the question, how do we generate the right data? So these are the two things that Data Gym, which is upcoming at iClear this week, is addressing, right? The two main issues is we should make it student specific, right? Because different models have different weaknesses, right? Different weak skills. So the data should be more targeted, right? Think of a classroom. So this is also related to an NSF AI Institute that we have on AI for education. So if you want the ideal classroom, right, every student should not be getting the same exact exam, right? It should be much more personalized individual tutoring where depending on the weaknesses of individual students, right, you want to give them more exams or more questions or more examples to train them for those weaknesses, right? You might be good at linear algebra, right, versus someone might be good at calculus. So there's no point giving the same kinds of questions to everyone, right? So that's sort of the motivation here to be student specific. And the other motivation is that there is a whole missing notion of temporality in data generation models, which is that once I have figured out some data and trained the model again, now there will be some other weaknesses that will pop up, right? Because now that previous weakness, right, has gone, but maybe some old weakness, right, that was not a weakness became a weakness now. Or something harder has popped up as the next weakness that we should address, right? So these are the two things that Data Gym addresses. So in briefly again, I'll show the main sort of logic here, where, like I said, agents in Data Gym are trying to improve a student model on diverse open-ended tasks based on automatically discovered model weaknesses. So think of it as an RL style pipeline where the student model comes in at time t step. You have an evaluation component, which basically I'll discuss how it's represented, but think of it as the state representation. And then the student model performance, right, as the state goes into an agent, a data generation agent, which then creates a data generation policy that is converted and outputted to a data generation plan, right, which the data generation engine takes in, creates training data, And this training data, right, is then used to update the student model to the next time step t+1. So we actually in the paper, if you check, you'll see that we have 15, 16 iterations of this where the model keeps getting better because it's figuring out different weaknesses and addressing them. And the main component of this paper that was challenging is how do you actually define the state, right? The weaknesses, because in very toyish tasks, you actually know what the skills are, right? Suppose I'm playing a Minecraft game, then cutting wood, picking up an axe, right? These can be the skills and you can actually already create a vector, right, of skills and their performance. But that's not how the real world tasks operate, right? So the biggest challenge of actually the setup is to be able to discover the skills automatically. Right, so here is sort of like a high-level version of how you learn skills, right? You have two steps here. You can ask an LLM to first label, for example, the questions in the task with different skills. And then you also ask the LLM to now go and cluster those skills. And then you repeat this process, right? And there's a lot of other steps that you can look at the paper for. But the basic idea is that you follow these two steps, right? And in fact, this is an example that's completely automatically generated for the multimodal BQA kind of task, where the data MGIM agent automatically understands that the first skill can be animal identification, and then there'll be sub-skills like identifying animal characteristics versus animal diet patterns. It'll also generate images, questions, and answers, right, for these different parts of the subtree. This is obviously like only a part of the tree that's generated. And then on the other side, it might generate another part of the skill tree, which is about object attributes, and then it might have sub-skills like shape transformations versus color and texture, and it will also generate images, questions, and answers. So this is just for multimodal reasoning. We also show this for many other tasks. This is, for example, the skill tree that's learned for math. It will learn a tree like function analysis and manipulation, which will have sub-skills like inverse function identification and asymptotic behavior and analysis, and it will also generate math problems and answers. Versus on this side, it could be probability and combinatorics, right? Permutation combination versus Markov chains. So I encourage you to check the paper for details, but basically we have so far covered 5 data sets across 4 domains, right? So multimodal GQA, multimodal natural bench, tool use M&Ms, math reasoning, as well as code reasoning. And I think there's some interesting plots that you might be interested in the paper, like I said, where we also show how we do this for 15, 16 iterations, right, where the model keeps finding new weaknesses and addresses them through data generation. So it sort of iteratively improves over several iterations. Obviously, at some point, it starts saturating, right, when there is not, like when the sort of, this sort of sweet spot of the challengingness of the weakness that's now remaining, right, is not part of the current capability of the model. Okay, so that was part 1. Let me keep around 10 minutes briefly for part 2. So now I want to discuss the same thing, right? How to do trustworthy planning agent development, but for a very different task like multimodal generation. But the goal will be the same, right? It's all about how we can make them more interpretable, safe through planning, programming, right? But the kind of planning and programming will look different here. And I'll just cover 3 papers here. But the goal is, like I said, to have interpretable, controllable multimodal generation by using LLMs as planners or programming agents. And what are the 4 different advantages of this? The first advantage is that it makes these multimodal generative models more understandable, right? So if you basically have used any kind of image or video generation model, right, it's very frustrating where you're pretty much trying your luck, right, in terms of, okay, let me change this word in the prompt, or let me make it longer, or let me keep doing hit and trial, right? So in some sense, it's not just about understanding of the human, right? So what I'm saying is the planning and the layout planning of image and video generation is not just making the process more understandable to humans, but more understandable to the model itself, right? This is also a very understudied problem, but there have been papers, right, that have shown that for language generation and other generative models, most generative models are really bad at even understanding their own generations, right? If you ask them to do some kind of understanding or classification or prediction tasks on their generations, right, they're failing pretty spectacularly. So that's the understanding part. The faithfulness and trust part is there. And the best part is the human in the loop control, as I'll show, as well as out of distribution. So the very simple paradigm that we followed, right, so is because of the same background or motivation that I mentioned, that text to image generation, right, is very black boxy. So if I have some examples like 2 Pikachus on a table or a truck is behind a motorcycle, right, you'll see some good visual quality, but very quickly you'll see very big important semantic issues, right, lack of fine-grained layout planning control, interpretability, faithfulness, right, hallucinations, out-of-domain issues. So what we did is, this is something called visual programming or planning for step-by-step text-to-image generation. What we proposed is that we should basically treat this as a layout planning problem, where you first ask the LLM and teach it to convert the caption to some kind of objects and counts. And then you basically ask the LLM to also learn how to generate the bounding boxes of these objects. And this is where its prepositional and language capabilities come in, right? Because if I'm saying 2 Pikachus on a table, that will generate the average y coordinate of the Pikachu boxes, right, to be higher than the average y coordinate of the table box. Whereas if I had said 2 Pikachus under a table, right, it would do the reverse. And then you bring in the last part, which is the infilling. So in terms of more real examples, right, you can check the paper, but basically the 3 biggest issues that we showed, right, instead of just showing FID and distributional metrics, right, that are also very black boxy, we first showed that the 3 or 4 biggest problems in image generation models is things like counting skills, right, spatial relationships, as well as scale. So stable diffusion, right, kinds of models versus, you can see if we go through programming and planning based methods, right, can have a big improvement. And if you look at some examples here, like 3 boards, right, stable diffusion will create a very nice looking image, but there's no notion of 3 here, right? Whereas if you force the model to plan first, right, and right, be faithful to the count 3, same thing for truck is behind a motorcycle, you already can guarantee that the box for motorcycle and truck will have the relationship behind. And then scale, right, remote bigger than a cat is some out of distribution scenario here, right, which models have not seen before. Whereas in this planning based approach, you can actually already make sure that the remote box is bigger than the cat. And in fact, if it's not big enough, right, you go into the image, change the size of the box, and then ask it to regenerate it, right? That's basically where the human in the loop comes in. I'll also show you the more complex version of this for long video generation. But before that, I want to flip the problem. So what we've also done is we've also shown how to use visual planning or programming to improve evaluation protocols, right? So if anyone works on image or video generation, you know how challenging it is to evaluate, right, these models. So same thing here, right? It's very black boxy. I can send it to some kind of alignment model like clip or blip, and then some random number like 0.769 comes out. I have no clue, right, what to do with that. How did the model compute this score? What does it mean? How do I compare it to other scores? But most importantly, how do I understand what are the weaknesses of my model that I can then, right, improve upon? So in VP eval, what we did was, if you have a very complex prompt like a white slope covers the background, while the foreground features a grassy slope with several rams grazing and one measly underdeveloped evergreen in the foreground. Again, right, code generation comes to the rescue here, where you'll try to teach an LLM to convert this complex prompt into different kinds of modular evaluation programs, right? So presence of RAM, presence of evergreen, count of RAM greater than 1, but count of evergreen exactly equal to 1. And then whatever doesn't fit into the programs, right, can be converted to open-ended visual question answering. So the best part here, like I said, is that you're not just getting some number like 0.769, but you're actually being told which parts of the generated image, right, were correct versus incorrect. So the presence of the RAM was wrong, the presence of evergreen was correct, and then the count of evergreen was wrong because it was supposed to generate exactly 1, but it generated 8. And in fact, it will also show you the bounding boxes, right, for the, or segmentations now, right, for the generated extra evergreens, and then the VQA side. And then the last example that I'll cover is called Video Director GPT, which is about consistent multi-scene video generation via LLM guided planning and reasoning. So this is again where we showed that this was the first paper trying to do long video generation, and the biggest challenges here, right, this is long before Sora, and the main challenges here are, right, that when you're trying to do long video generation, first of all, fine-grained layout planning, right, across the long video is crucial, and equally crucial is consistency, right? You want to make sure that the characters, when they appear and disappear and reappear, should look visually consistent. So this is again where we asked the question that can we use LLM guided planning or reasoning, right, because of the co-reference and other capabilities in them. So this is what Video Director GPT does. First of all, it goes into the video planning stage, where if there is an example like a hungry cat finding food, it will try to generate sub-scenes like a cat is lying down on a bed, but it will also generate the whole visual scene, right? It will generate the bed bounding box versus the cat bounding box, which is a little bit longer, right, horizontally. And then when it says then it will generate, then she gets up, and it will change the bounding box, right, to a more sort of longer y coordinate, right, because of getting up versus lying down. and then it'll also learn when should new entities come in with a new color, right? So the snack entity comes in. So basically, think of it as like visual co-reference resolution. I don't know in this, right, in today's generation, like who has worked on co-reference resolution or even heard of the term. But basically the idea is that when you're using a lot of, right, things like mentions of common nouns and pronouns in language, right, you have to learn which pronouns and common nouns, right, and proper nouns create the same entity cluster, right? Which pronouns refer to which noun, right, in the previous sentence. So same thing here, right? You want to do this visually, where you want to learn that this orange box in the third scene actually refers to the same orange boxes in the first and second scene here, whereas the green boxes, right, are referring to this entity here. And then in the second stage, the video generator comes in. It takes all these fine-grained layouts being generated and the consistency color groupings. And then we took a single scene video generation model, went inside its spatial temporal blocks, and then we inserted these new guided 2D attention modules, which allow us to forcefully, right, teach the model to respect the layout constraints that we have generated in the first stage. And so the best part here is that only these guided 2D attention modules are trained. Everything else can be kept frozen, as well as we share the parameters between the same colored, right, boxes for consistency. So all of this was being able to get trained in 4 A100s or 8 A6000s, right, very academic scale. And I'll show you some more real examples here. So basically, there's more examples in the paper and website, but this is some initial understanding of basic physics in terms of throwing some, like gravity versus distance and zooming in, camera motions, right? Static objects, only the camera should move, not the object, versus dynamic objects where the object and camera can move. It can also do these sort of multi-sentence complex stories which are basically out of distribution, right? Never been seen before. Like a mouse is holding a book and makes a happy face, pulling petals off the flower, holding a flower by his right paw, right? So if you see, like, this is all very fine-grained sort of control where it is holding this flower in its right paw, right? It's reading the book, and the mouse, right, is also visually very consistent. And then to me, the best part here, like I said, is all of this paradigm is not just making things more understandable, more faithful, right, but also allowing human-in-the-loop control, where I can go inside the generated video, and if I don't like something, like some part of the video that was wrongly generated, I can go and change the size of the horse or the background, right, to grassland or night street and so on. So I'll sort of conclude here. I know because we are tight on time, but there's also 2 new works that we have out recently as an extension to Video Director. One is called Dream Runner, where we basically showed the power of retrieval, but for video generation, right? So in some sense, if there's a very complex motion called, let's say, a cat or like a witch is sipping tea, right? You don't want to be able to generate new complex motions from scratch. So we showed how you can find the best kinds of related videos online and then extract only the motion prior from those videos and be able to insert that, right, to generate new motions. And then the other one is called Video Repair, where we basically showed that when you've generated a video, you can actually figure out its weaknesses, the wrong parts of the generated video, and then change the noise function to only regenerate the wrong parts of the video, whereas you can preserve the correct parts. So let me conclude here some of the things that I sort of shared today, right, and also things to think about moving forward. One is the trade-off of monolithic pre-training, right, versus modular structure. So hopefully, right, in sort of the brief time slot, I was able to cover and convince you of things like faithfulness, efficiency, interpretability, human-in-the-loop control, right, out of distribution, a lot of advantages. For the first part of the talk, right, things moving forward that we have to think about when scaling up multi-agent communication will be things like long-term factors of, like, for example, reputations, right, of different agents over time, right? Are they building a positive or negative reputation over multiple tasks, right, across a long time span? Mixed cooperation scenarios like negotiation, as well as, right, mixed capability scenarios like system 1.x, like we had a paper on how to combine fast versus slow thinking. I skipped most of the other ones, but I think the last 2-3 bullets are also very crucial, right? Continual learning versus unlearning, right? So so basically we have also a lot of work on these 2 topics that I'm happy to chat about. But the main goal here is that when something very small, right, changes in the model's knowledge, what we are doing right now, right, is very inefficient. So can we have a very fine-grained control in terms of being able to address and change something very specific in the model when either that information gets outdated or new information comes in that needs to be compositionally right, added to change the current information. So this is where continual learning and unlearning, right, model editing, model knowledge localization methods come in. So I'm happy to also chat about those offline. Thanks.
Thank you very much, Prof. Bansal, for exciting works that you've done on the trustworthy planning agent and for sharing them with us today. So we have time for some questions. Any questions for Prof. Bansal? So let me start with one question. So thank you for sharing many exciting work, including the one that we presented at ICLR soon.
Yeah.
So I'm wondering, like, there is a graph that you show that there are many tasks that you have tried for agents to learn new skills.
Right.
And I noticed that the improvement for math and also for code is a bit lower than the others.
Right.
I wonder if you can share more insight into
why. So math and so that's a good question, right? So math and code are much more sort of saturated, also because in some sense the data there, right, has been always much more available. And also if you look at reward models, right, math has always had the best kind of reward models. So the base models that we are starting with, right, are usually much more strong at math and code. And also the skill discovery part, right, is easier there. So once you have figured out some skills, right, then we are also showing that over multiple iterations, there's not much else left to improve, right? So it also depends on how many iterations you can have to get iterative improvements.
Thank you very much for that additional details there. Any question?
Thanks for the great talk. Just now you mentioned about multi-scene video generation. Just want to understand, how do you ensure the consistency between different scenes?
Yeah, so that's what I was showing, right? I sort of covered it a bit quickly, but basically the model is learning, when it's generating these fine-grained layouts, it's also learning sort of co-reference resolution, which means that it's learning which boxes across scenes. Like this is obviously a small, simple example, but there's sometimes 30, 40, 50, 60 scenes, right? So over time, it's learning that this box in scene 1 is the same as this box in scene 11, which is the same as this box, right, which is somewhere very differently in the location in scene 31. So it basically makes sure that visually, right, the model learns to generate visually very consistent colors and shape, right, for those boxes, even if they are very different scenes.
So there is no further question. Let's thank Professor Bansal again. There's one question there. Sorry.
Okay, thank you for the great talk. So I have a question about the generation. Since we also do some generation, I think a very big issue is that you can hardly follow the prompt to generate something. So I want to seek your suggestions for this. Whether I think you use some agent to control the generation. So any tips for this? For example, use the agent to help to overcome these limitations. Thank you.
So let me maybe just briefly show you something. So this is, yeah, I mean, I sort of took out a lot of things just to make it nice and short. I usually am always over time, so I'm a bit surprised that I'm on time today. But I think I overcompress them. But yeah, so this is, oh, I guess there's no internet. Is there a Wi-Fi here quickly? Marriott, okay, maybe it needs login, I'm not sure. Anyway, so I mean, if you look at this word called video repair, basically it actually goes and checks which parts of the prompt were correct versus incorrectly matched or generated. Yeah, it's much easier if I can show you briefly. So basically it will use our evaluation metrics, right, that I showed you, VP eval, to figure out which parts of the model generation were correct versus incorrect. And then, yeah, so I can show you here. So this is basically what it's doing. It will, if suppose the prompt is 1 bear and 2 people making pizza, so then it will go inside this model. So it will figure out that because of this prompt, right, 2 bear and 1 people making pizza, it will use it will basically use our evaluation method to figure out which parts of the prompt were generated correctly versus incorrectly, right? So it will figure out that the bear was generated correctly, but the people were missing. And then what we'll do is it will refine the prompt to say one person making pizza because, right, it knows that the half of the initial prompt was already correct, right? One bear and two people making pizza. And then it will take that refined prompt as well as it will also learn some parts of the noise to refine versus preserve. So it knows that this part of the video was already correct. So this part of the video will not be regenerated and it will be kept as the same, whereas the rest of the video will be allowed to regenerate. So this is a very targeted way of bringing everything together, where if you use our VP eval, and Davidsonian scene graph kinds of evaluation methods, it will tell you exactly which parts of the prompt were correct versus generated incorrect. And then it will refine the prompt for only the remaining incorrect parts. And it will also go to the noise level, for the diffusion process and make sure that it doesn't regenerate the parts of the video that were already correct, And it will only regenerate the parts that need to be corrected. So this is sort of bringing everything together in terms of not trying to make everything regenerate from scratch, because then, like you said, there's no control in terms of what parts of the prompt were correct versus incorrect.
Let's thank Professor Bansal again. Thank you.